Welcome to the new session. This session is about the algorithms which we are in the initial stage. We have discussed a few algorithms. The algorithms which we have discussed here are Diffie-Hellman, RSA, and Rabin. So we are about to discuss the remaining two algorithms in this session, that is ECC and ElGamal. So ECC is nothing but elliptic curve cryptography. See, as we have discussed in the previous sessions, Diffie-Hellman key exchange algorithm is utilized for the session key, which is utilized to avoid man-in-the-middle attack, only to generate the session key. RSA is utilized for both encryption and decryption also. At the same time, we are going to generate the key pair, that is public and private key combination. See, we'll generate public-private key combinations, and also we can do encryption, decryption. In the similar way, the Rabin cryptography also will do the same work, like we can generate the key pair and also encryption and decryption. Similarly, the two other algorithms also. Now, the elliptic curve cryptography is a very important, because with a smaller size, we can give more efficient security. See, RSA and whatever the crypto systems which we have discussed, those algorithms must have a larger prime numbers, which will be costing us more. And depending on the size of the key only, our security will be dependent. If as much as the key size is increasing, the security also increases. But the main advantages of ECC is nothing but, even though the key size is very small, we can give more security by this ECC. So let us move into the topic now. This elliptic curve cryptography will be evaluated with respect to one graph system. See, there we have to give a curve. So where this curve will be denoting on the x and y axis randomly, right? See, when we are going to utilize this, n number of adversaries cannot understand what may be the curve, which may be the curve you have utilized in the algebraic structure. So they will be not understanding what may be your exact point, from which point you have taken the outcome called G. Okay, so let us see this. See, as you can see here we have given one graph system. So let us draw the other one. Okay, so symmetric graph system. See, this should be symmetric type. Symmetric is nothing but the x and y axis must be variated in the positive direction, and the negative direction, it should be equally given, right? Now, when I draw one line like this, see, we will be given with 3 points which will be pointing on the curve, right? So these 3 points are very important. After these 3 points, I will be selecting one value called n. After these 3 values, we will be selecting one value called n. So this n value and whatever the g value, at most value we plot from the graph, will be playing an important role in the encryption and decryption procedure of the elliptic curve cryptography, right? See here. So we have to select one elliptic curve parameter, that is a, b, and q. Right. See, after this, we have to go with one point, that is that point as g. See, I have just shown on the plot. So we have to select the larger value n. See, after the curve ends, I have given with one larger value n. See, this n value will be deciding what is the g value. Now, after this, we have to select one private key which must be less than my n value, which I have plotted after 3 points. After 3 points, whatever the point, end point we have given with one value, right? So if this is x and y axis, so this is the end point. So this n value will be playing an important role, right? Now this n value will be deciding what is the private key of a user. I mean, less than any value you can choose. Similarly, NB also we have to choose. After choosing this, we have to find the public keys of A and B. So how to find the public key of A? So just take the private key of A and utilize this plotted value G. Similarly, utilize the private key of B at the receiver side, and you utilize the G plotted value G, so that you will be getting PA and PB, right? See, after getting this PA and PB, you generate the session key also, K, which is common to both. So this is nothing but utilize your private key and opponent's, I mean the receiver's public key. Utilize your private key and utilize the sender's public key. See, by this, Alice and Bob will be, both the sender and receiver will be having equal probability of creating the private keys, public key combinations, and also the symmetrical, I mean the secret key, which is the same to both the sender and receiver. After this, the procedure of entering into the encryption and decryption. So in the encryption procedure, nothing but we have to select one plain text M, encode that with the value which is plotted. So let us, after encoding, so whatever the value we get, that as PM. So this is the plain text. I mean, on the curve, we have to plot our value, plain text M, and we are calling that as PM. Okay, send this PM onto the network. Got it? So while we are sending this, we are going to send along with the public key, I mean the base point, whatever which we have. See, G is the base point, right? So CM will be having all the information. I mean the CM is nothing but the ciphertext of the plain text PM. Okay. So at decryption side, whatever they have received, see whatever they have received, PM plus KPB. Okay, as I am encrypted with PB value. So what is PB? Public key of the user, right? Public key of the receiver. So we are encrypting with respect to the public key of the receiver and with some K, a positive, random positive value. Now send that into the network. Now we have our ciphertext into the network. Now utilize your secret key along with the plotted G value and also your K value to decrypt the value. So how to decrypt it? See, we have given with PM. See, this is a value which we got from the sender. PM, K, PB. Okay. So PM, K, PB. Now user B will be utilizing their own private key to decrypt it. Now, as per PB, what is the value of PB in the previous session? What is the value of the PB? See, just take this NB into G. NB into, I mean PB equal to, just substitute NB into G. NB into G here. Just substitute PM plus K G into NB minus K G into NB. So the positive and negative gets cancelled. The plain text which we have will be remaining one. Okay. So this is a procedure to work with the elliptic curve cryptography. I think you got it, right? So let us move to the another algorithm. So the algorithm is ElGamal cryptography. See, ElGamal cryptography is very simpler, which is almost similar to Diffie-Hellman algorithm itself. Okay, so along with this, we are going to, I mean, along with the utilization of Diffie-Hellman algorithm, we are going to utilize encryption decryption procedure also in ElGamal cryptography. The inventor of this is Teher ElGamal, and key size is 5 to 12, minimum is 5 to 12, and we can extend up to the mark. Okay, so this is the ElGamal cryptography. See, ElGamal cryptography is as similar procedure as the Diffie-Hellman itself, but extra point which we have to note here is we are going to encrypt 2 times. Okay, so the ciphertext which we get will be encrypted 2 times. See, once we'll get one ciphertext and again we'll do another ciphertext. We will send these 2 ciphertexts to the receiver. So first, as similar, choose one prime number, find the primitive root. Then after, you go with the selection of your private key at the receiver, I mean sender, and calculate your public key and exchange to Bob, right? So this is what we are doing, right? So public key is nothing but the prime number and the primitive root and your YA will be shared into the network. XA, which is confidential, will not be shared to anyone. I mean, sharing in the sense, we are not sharing to the network. We're just arranging every public key in the public key ring distribution center, right? Now, M is a plain text, right? And the plain text which we're choosing should be less than the Q. Now, choose one random integer, then calculate K with respect to sender's public key. Then you calculate C1 with respect to the primitive root sent by the sender, alpha to the power of K mod Q. Now, calculate C2 with the plain text value and also K value, whatever the K we have calculated just now with respect to the public key of the sender. Just calculate those two with mod primary key, I mean prime number. So whatever the values we get, just transfer to the receiver. Now, at receiver end, what we are doing here? So just take C1, then to the power of its own private key XA mod Q. Next, take C2, whatever the K we got, do its inverse process, apply with C2, do mod with the prime number, so that we will be getting back our main plain text back. So this is the procedure we apply for ElGamal cryptography in asymmetric cryptographic system, right? So this is one of the small example which I'm about to show to you now. See, now I have chosen Q, my prime number as 19. Then I have given with a number of primitive roots. Among them, we have chosen 10 as a primitive root. See, primitive root concept we had discussed in the mathematical of cryptography. Just go through it. In RSA also we have done. Now, find your public key. Send your public key, prime number and primitive root to the, your public key is ready now. So you just release into the network. Now we have chosen at the sender side, we have chosen our plain text. So after choosing the plain text, you go with the finding of K first, then C1, C2. So whatever the values we get 11 and 5, you just forward to the receiver end. See 11 and 5, you just forward to the receiver end. So the decryption procedure, just will take C1 first, calculate K with respect to C1 to the power of XA. Okay. So Bob is R9, right? Your receiver's private key. Then you will be getting one value 7. Take this 7 value and your C2 value. Okay. So you just calculate everything. Your plain text 17 will be back. See the plain text which I took m equal to 17 and the plain text after decryption we get both are same, right? So this is a small procedure which we follow for ElGamal cryptography. So this is the end of all the cryptographic algorithms in the asymmetric type. Asymmetric is also called as public key. So this is a small comparison. See where RSA can go with encryption, decryption, and also it can generate the key pair combination, right? And elliptic also do the same. Diffie-Hellman cannot do that. It can do only key pair exchange, right? Key pair, just the session key. ElGamal also will do all the things, and we have extra thing, DSS. This is not there in the syllabus. That we'll be discussing in the next unit. Okay, so these are the end of third unit. If you have any doubts, just feel free to contact. Thank you for listening.